webinar, this time with PlanBee. We have the pleasure to have Marco Juliani with us. Marco is a design computation specialist at Callison CRTKL. He lives in London, and well, he has his master's from the Bartlett, from the UCL, where he also sometimes teaches Unity3d and C# fundamentals. And today he's going to present a new app for Rhino. This is PlanBee, with which you can showcase the analysis metrics we can extract from floor plans and well, leveraging space syntax concepts, as well as producing custom analysis metrics. The webinar will showcase how to uncover some of the qualities inherent in spatial configurations. In doing so, we can make more informed design decisions, produce feature maps, as well as start to place programmatic elements in an experimental manner. Marco will start with an introduction, then he will do a live demo, and at the end of the webinar, there will be time for questions, but feel free to place your questions already on the chat. My colleague Carla Sologuren is there monitoring it, and I will also collect the questions for the last 20 minutes of this session. Remember that this webinar is being recorded, so right after it finishes, it will be available on our food4Rhino playlist on the McNeel Europe YouTube channel. So Marco, welcome, and you can start now with your presentation. Thanks for being here.
Thank you for having me, Carlos, and thank you to McNeel and food4Rhino. Let's jump right in. I guess you can't see my screen yet. Give me a second. Share screen.
Not yet.
There it is.
Now, perfect.
Okay, well, thanks for having me again. And as you said, I do computational design at Callison CRTKL, and PlanBee for Grasshopper is basically a side project that now is starting to use more and more for floor plan analysis, but it's very much kind of a work in progress and a side project and something that hopefully people find useful. So I did not study space syntax formally, but I became acquainted with some of the metrics, some of the analysis. So if there are experts in the audience, feel free to send comments, questions, corrections. I think PlanBee is open to be modified. So it's, yes, take it as it is, and it's a work in progress. So I am happy to receive all feedback. So what is PlanBee? It basically is a floor plan analysis plugin that enables you to analyze each cell in a floor plan according to various different metrics. So in that sense, it's a static analysis. It doesn't run dynamic agents, or time doesn't really matter in this case. It's just like static analysis. It takes into account the configuration, the walls, the core, the perimeter boundary, these kinds of things. So it borrows from space syntax in that there are some metrics that are space syntax metrics. And some of them are just custom. Like one, for example, is just a daylight metric that takes into account an analysis period, and it tells you how much sun hits the different parts of the floor plan. Another one's like the COVID metric, tells you like how compromised the floor plan is based on a very simple kind of way of measuring that. So again, the whole point is that we can add more metrics, and you can create your own, and then like you can create like a rich kind of stack of information that corresponds to the floor plan. So if you go on food4Rhino right now, I've updated the second release of PlanBee, and you will find a new GHA file as well as some sample files. And I'm basically planning on uploading this PowerPoint or as a PDF format to food4Rhino, so you can use this as a user guide. Because I think there is plenty of annotation here that can be quite helpful later. Or you can rewatch this video, of course. So what can we use this for? You can use this again to calculate different metrics for different parts of the floor plan. You can then plug in all that raw data into some kind of unsupervised machine learning or some kind of data analysis. You can perform like data analysis on it, stuff like that. And last but not least, there's a little component that enables you to take sketches and convert them into kind of vectorized geometry. And in that way, you can draw stuff, you can upload it, and then you can get that analyzed. So that's one of the fun ones. Let's see. So the new features are, now you can create analysis grids in a very simple way. I don't know if you were familiar with the original way, but there's just one way to create kind of analysis grids. Now it's more flexible. There's additional metrics. And again, there's the image processing component. That should be fun. So yeah, this is the second round. The first version of PlanBee was released January of 2020, but now this is kind of the updated version. And we shall see. Maybe there'll be a third version. So let's see what metrics we can come up with. So I'm just going to show a few slides on space syntax. Space syntax, for those that are not familiar, is a set of methods and kind of concepts that are applied at the urban scale as well as at the building scale, pioneered at the Bartlett in the 70s. There's also a consultancy called Space Syntax. And it's an ongoing thing. It hasn't been frozen in time. Like the theories continue to evolve. So in that way, it's kind of hard to pinpoint exactly what space syntax is because it's many things. But the main thing we need to know is that we can conduct spatial analysis kind of at the urban scale as well as the building scale. And PlanBee focuses more on the building scale. And so just to talk about some of the building blocks of space syntax, space syntax uses this idea of graphs, so nodes and edges, to kind of describe space. But there are other building blocks such as like discrete cells. But even those, when you think about a field of cells, when you start talking about how they're connected, that also describes graph. So these are some of the these are the building blocks of space syntax. And then graph, we know graphs because meshes are graphs, vertices and information describing how the vertices are connected. That's what a graph is. And just one more slide on graphs and meshes. And you can do more digging on this yourself. In PlanBee, we don't go too deep into graph theory, but all you need to know is that the analysis grids that PlanBee uses basically has a connectivity information that helps, the engine, the PlanBee kind of components kind of determine pathfinding information and stuff like that. So this is one of the final two slides on space syntax. But again, this idea of isovist, which if you're not familiar is a viewshed, PlanBee uses that extensively. It has to do with calculating the viewable kind of polygon from any given point in space. And again, kind of PlanBee utilizes this concept quite a bit. And the final slide on space syntax is that there are other space syntax software out there. DepthMapX, developed at UCL Bartlett, isovist.org, and even a Grasshopper toolkit that's called Decoding Spaces that kind of exposes a whole range of analysis metrics on kind of floor plans. Let's see. So now we can switch over to the PlanBee workflow. And in a nutshell, what you have to do in order to use PlanBee is you have to create an analysis grid. In order to do that, you have some flexibility. There's some flexibility. The bare minimum is to give it a perimeter boundary to describe your floor plate. And of course, a resolution, like you need to tell it, I want my grid to be 1 meter across, 2 meters, 1.5 meters. I think often 1 meter is good because it can be less, but it's basically you want the basic unit of space that describes kind of the human experience, because anything less than that, I think it's just kind of not worth it, and it's more computational costs. So you want it to be fast and representative, right? So you can add like cores, you can add holes in the floor plan, you can add partition walls, and then you've constructed your grid. Then you have your grid. You can analyze various different metrics. And then you have a whole lot of kind of raw data coming out of those metric components. And then with that data, you can create you can do a data analysis and kind of do whatever you want with that. So that's the general schematic of how you use PlanBee. So just quickly kind of outlining the different metrics. So again, a work in progress. So distance to perimeter was meant to be kind of a proxy for daylight, but then I built out a daylight metric. Then there's an attractor metric that has to do with visibility to landmarks. There's a COVID metric. There's an exit axis metric, which computes the distance to the nearest exit. Exit as defined, like you can define where the exit is or the exits. Path more traveled. I mean, so these are all different metrics, and I encourage you to explore them. You know, each component is basically a metric. So have a look, and we're going to go over some of them right now. So all that to say, like when you stack all these metrics together, you have kind of a field, a stack of different metrics that start to describe each cell on the floor plan. And that can potentially be very useful information if you can like figure out what to do with it. At the moment, I'm applying a self-organizing map to it, which is like an old school unsupervised machine learning algorithm that I learned at the Bartlett last year. And the results are kind of experimental, and it doesn't give you a finished floor plan by any measure, but it's kind of a starting point at what you can start to do with this data. And so this is what I mean. Like you can use, like on the right, you have a self-organizing feature map, a cohoned self-organizing map. And in principle, what that does is it takes a lot of data that is described across like multiple dimensions, you know, and then it kind of reduces it to a two-dimensional plane. And it's a data reduction technique that you have a field of objects, and then in that field, you start to see kind of zones that are highly related to each other. So on the food4Rhino description for PlanBee, I've included a link that shows kind of a quick tutorial of what it actually does. But yeah, I encourage you to take a look at that. And then on the left here, you can use like k-means clustering to do something quite similar to that. So there are other, there's Proving Grounds, Lunchbox ML, and other machine learning tools that enable you to quickly plug in and get some results. If anyone else has, if you have other kind of techniques that you would like to see applied or that you can kind of suggest, please send that through in the chat. That would be cool. So now let's dig into actual PlanBee. So if we look at the components, we can start with the inputs, and this is the very first input. You can specify program areas as described here on the left. You can give a list and enumerate a bunch of programs and their corresponding areas. Similarly, you can give program features. So you can actually say, these are my programs, and these are the different features. So natural light, views to landmarks, proximity, visual connectivity. And then you can give them a normalized range. So you can say office, natural light is quite important. I'm going to give it a full 1 because the range is between 1 and 0. But maybe access to storage, not so important. Let's say views to landmarks equally important, so on and so forth. So you can give it like a normalized range that starts to describe how important each of these features is to a program element. And we'll see why that's important later. You can make use of that later. Second component, the second sort of set of components we're going to go over is the analysis grid. So this first one on the top enables you to specify kind of the areas and a whole bunch of detailed information about core. Do you want a dryer core? Do you want the core to be generated based on a least target, resolution, stuff like this? It gives you an area feedback of whether you're meeting your areas as described in the Excel spreadsheet, stuff like this. And then as you move down, you can just create like a sample grid with like just sort of a perimeter curve and some cores. And lastly, you can just like supply a perimeter boundary. So you have some flexibility in terms of how you can create your analysis grids. Then we have the daylight period component, which is one of the input components. And while I love Ladybug, often, I wanted something quicker. I just wanted to get the vector information and do like a proxy. Can we do an analysis that doesn't involve radiation or anything? Just like a quick raycasting study that tells me whether different points in a given scheme are getting direct access to daylight. So it's an overly simplified way of doing it, but this component enables you to extract a sample range of vectors very quickly. And after this one, I'm gonna stop and show like a quick demo. But this is the newest kind of component, and I think it's one of the funner ones. This is the one where you can actually draw a sketch and supply kind of the file path, and then and then you have to supply kind of the colors that PlanBee has to look for. And then once you've done that, PlanBee will kind of spit out a tree of polylines for you, each branch corresponding to a color. So that's kind of a limiting factor, I would say, because you would want it to just detect that automatically, but maybe for the next kind of iteration. So let's do a quick demo here. I'm just going to go over what we just went over. I guess you can see my screen. So I'm just going to describe very briefly what's going on. So basically, we have an area spreadsheet, and then we have the feature spreadsheet, right? And then, so again, I don't even know if this is worth going over. I just kind of went over it, but it's just since I have the file prepared, I'm just going to show you. So again, one way to create a grid, a second way to create a grid without any feedback, without any, with less detail. And finally, with this one, all you need to do, this one's more designed for corridors because, you can't supply a core, you can't supply any holes. So you could take a residential floor plan of a multifamily residential, for example, draw the corridor and start to analyze that as a space on its own. So that's what you can do with the analysis grid. Because we looked at the daylight one, let's take a look very quickly. So what this thing does, again, you supply an analysis period, it spits out some vectors. And what's kind of interesting is that actually it's, if I turn this on, it gives me kind of an estimate of like what direct sun rays are hitting kind of the cells, and so you get like a heat map from what's hitting it the most to what's hitting it the least. And in this particular case, I'm giving it a floor to ceiling height, and it's automatically offsetting that and creating kind of an obstacle mesh that is used for collision detection, right? So out of the box, without me having to do anything, it's kind of spitting out the collision objects, which is really handy, right? And additionally, we can add obstacle geometry. So if you have a building in front of it, you can just add that, and it will take that into consideration, right? So that's the demo for this one, and let's move on. I guess we can. It's kind of flexible here because this next slide has to do with the anatomy of these components. And as you just saw, these analysis components have a series of inputs. They have a Boolean toggle that says, auto color or not. And then the set of outputs are normally like a range of numbers between 0 and 1 that describe the different cells. And then there's other outputs like collision lines, or in this case, for the daylight component, there was an obstacle mesh, just so you can take a look and you can see what geometry is being used as the assumption for the calculation, right? And the only really important thing to take away from these anatomy slides is that PlanBee has this built-in override for drawing meshes. So that's how you get out of the box. That's how we're getting kind of these colored grids. So the thing to note is that if you have multiple components in one file, it's going to really bog the file down. This needs to be rewritten at some point to use like conduits or some other thing. So the only thing to keep in mind is if you have multiple components on the Grasshopper canvas, make sure to turn it off if you're not using it, because otherwise, very quickly, your Rhino file, your Grasshopper file is going to start to crash. So just something to keep in mind. I thought that was, yeah, definitely worth mentioning, because, you know, it could be frustrating if you don't know that and you just leave everything to true. So, so this is the one we just went over. Daylight. This other one is the attractor visibility. So you can add a series of kind of 2D lines describing attraction or landmarks that are around your site, and this component kind of computes the visibility to it and creates a heat map for you, and it spits out the lines as we discussed. Each of these components gives you kind of some kind of geometrical output, as well as a range of numbers that describe between 0 and 1 what the visibility is of each of the cells. So yes, this is the attractor component, and it's one that I've come across very often. That's why it was one of the first metrics, because I find myself having to calculate this all the time when we design things. Usually in 3D. For PlanBee, it was kind of, we're keeping it to 2D for now. The isovist metric, I believe the isovist is very well known. I think Grasshopper has a built-in isovist component, but in keeping with this PlanBee suite of tools, I want to get the normalized metric, the normalized number describing each cell and all that. So I built my own. So the polyline is calculated by shooting lines, right? You shoot lines kind of in a circular direction, and then you compute the distances of those collisions, and that gives you kind of the isovist. That's one way to calculate the isovist. There's a very similar metric that's actually very useful in space syntax. It's called neighborhood size, and I believe it's also called connectivity. So yeah, I believe so. So it's very similar to the isovist. However, instead of shooting a bunch of lines and calculating the combined distance of all those lines, you actually calculate the polygon that makes up your viewshed or your isovist. And so, so just a slightly different way to calculate the isovist that is used to kind of measure the visual connectivity of the space. And this can be quite useful. I mean, in space syntax, visual connectivity is kind of how you can predict how people are going to move in space when you don't consider anything else. So if you just consider the space itself, how the walls are arranged, how the corridors are set up, often the theory is that people tend to walk in the direction of their longest line of sight. So when you take that theory and if that's your premise, then neighborhood size can be kind of a good metric to have when evaluating these things, because again, it tells you what the visual connectivity is from each point. So in this case, the white means it's highly connected. The dark means less connected, right? So, okay, moving on, clustering coefficient. This is another one that less used, but I found it in this really good paper. Have a look at it. And basically, all it is it's a score that tells you how your visual cone is going to change as you move through space. So in this case, white means that it won't change much as you're moving through that particular space, but black is telling you that as you move through that space, your cone of vision is going to change very quickly. So it's just again, I just thought it was a really interesting metric, and that's why I've included it. Not sure. I mean, yeah, maybe not that useful, but again, I think collecting these metrics is interesting. Some people might find them useful, others not so much. And then the COVID metric. So this is a very simple one. I think this is not comprehensive at all, but it's one kind of proxy metric that would start to tell you is a space compromised. And the way this works is I'm keeping it very simple. I've seen other versions of this that are more involved, but for this particular one, shooting rays in kind of cardinal directions. And then if two or more rays that are 90 degrees apart collide with obstacles, then that cell becomes compromised. And so it's just kind of a lazy way to say, let's measure how close we are to the surrounding obstacle geometry. If we are kind of between obstacle geometry, then I'm calling it, compromised. So I think this little, I think these images start to describe what it's doing. And what's nice is, so you can work in metric, in meters, or in feet, and the component reads that, and it shoots either 6 feet or 2 meters. So that's convenient. Yeah. So again, you get your output lines as well as kind of your heat map and your values. So exit path. This is currently implementing a shortest path algorithm where you can give it, you can supply it some points, supply it, all your normal kind of inputs, and then you can measure the shortest distance from any point, any cell on the floor plan to these kind of exit points. And so as an output, you get a tree where each branch corresponds to the paths from each cell. Each branch corresponds to a cell. So if you have 2 exits, you're going to have 2 polylines on that branch. If you have 3 exits, you can have 3 polylines on that branch, and so on and so forth. So it's just kind of a quick way to compute the shortest path. And similarly, this is a very similar component, but rather than just outputting the raw values and the polylines, it actually counts which cells are being traversed over the most, and then it creates a heat map, kind of a usage map. And the metric that gets output here is just how used is it. This is kind of this is a made up one. Basically, all I'm doing here is supplying it a number of points on the floor plan. So maybe it can be like the number of rooms that you have, and then it's just literally calculating the paths between those points, and not just the paths, not just like the curves, the polylines that you would take, but also the frequency of how often the cells get used. So that's an interesting one. And then finally, so I'm going to show this slide, and then after that, I'm going to show a quick demo. So this is the Cajonen self-organizing map, and this is kind of at the moment experimental and not particularly useful. But I think if the hyperparameters, if the kind of inputs get calibrated right, I think it could, in principle, produce something interesting. So yes, there's a lot of inputs, and in the end, you get kind of a zone map like this, where each color corresponds to a different program, and so yes, you get that output in the form of a tree of cells, and the weights, and kind of you get like feedback of how your component is running. And so yes, play with it. I've got some people have emailed me that are they're like trying to figure out how it's used. I encourage you to play with it. It's once you get the input set up properly, it could be fun. So here we go. Let's open this file. Okay, so and I guess I mentioned it before, but if you have multiple components in a file, it can get heavy pretty quickly. I mean, these components are some of them are doing some pretty heavy lifting, and some of them have been optimized for like task capable, so they're running, they're doing parallel computing, but they're still heavy. So some of them are pretty heavy still. So let's go back. So the way this one works, this is part of the sample files. So all the files that I've shown, and many of the files that I haven't shown, are on food4Rhino. So have a look at them. But this is what we discussed earlier. So we're giving it spreadsheets describing the program and the areas and the features as well. And then we're creating kind of a grid, right? So then we have a very kind of fine grid, and I should probably make it more coarse because if we want this to run a little faster. Okay, and that took a minute because it's calculating all these analysis metrics. But then you have your voxels, and I forgot to clarify this, Carlos. Sorry about that, but these are really pixels because right now it's all two-dimensional, but voxels is a 3D term, right? So yes, at some point we might do pixels. It could well be that we start to create like 3D maps of this stuff, but for now, PlanBee is all 2D. So when I say voxels, I really mean pixels. And for now, I mean rectangles, right? So they're rectangles that have connectivity information, but so that's just to clarify. And so let's take a look. So I have my neighborhood size component, which is outputting kind of the areas of my isovists. I have this perimeter component, which is a very kind of basic one, because all it does is it computes distance to the perimeter. And then I have my attractor one. And I have my daylight one, and I have my COVID one. And yeah, so I have like 5 different things going, right? I have 5 different metrics, and I'm getting their normalized values. So normalized, normalized, normalized. In the end, I end up with a tree where each branch represents a cell, and each item represents one of the metrics, right? So I have 5 metrics per cell. And in this case, 725 cells, right? And when I have all that data, I can finally start to kind of make use of this component. So in this case, this is just the reset, run, optimize is kind of a test feature. So it doesn't do much right now. You can give it your program names. In this case, right, seven programs. Each of these programs has a program area, and I'm getting these from this component back here, names and areas, and program data, right? Program data is the feature information that we described. So for that, please refer to the features, program features, CSV. And so I have my program data, which describes the features, the desired features of my program. And then I have my voxels. Number of metrics in this case is 5, because again, we're supplying 5 different metrics. So that's 5 metrics. And then this is the good stuff. So this is actually the program data. This is all the normalized information that kind of comes out of all this analysis. And then the resolution, which again, and there's a hyperparameter called radius multiplier, which is, if you get into the Cohonen self-organizing map algorithm, basically it operates with kind of a radius. And so basically it's a field that gets initialized, and then there's each node, there's like a system where the different nodes in the field get initialized, and then they get recalibrated to kind of find their place in the field where the features are most present. And in that way, there's kind of a radius that you can manipulate or not. And in this case, this parameter is kind of being exposed, so you can kind of play with that. And then finally, this is an important toggle. This is the display SOM. And display type, you can actually display different aspects of this thing. So depending on what you're feeding, 0, 1, or 2. So 0 is like the discretized SOM, where you get like program colors. The second one is kind of, you get the best matching unit multiplier. And the second one is kind of the weight, the node weights, the raw weights. So again, the only useful one for now, let's say it's the program one. And then you get some display labels. So if you turn this on, you'll get like the labels describing the program. Yeah, so when we run this thing, you'll see that I can hit my kind of restart button, set this to true. And then for now, I've limited it to 150 iterations. So, so it doesn't run forever. So if you forget to hit kind of false on run, it will stop on its own. And so let's say for now it's done running. And what I'm able to do is I'm able to turn on the display SOM. And in this case, it will, I can see my program voxels. So if I start saying I want this tree branch, oops. So again, each branch corresponds to a program. And so in theory, you can imagine, if this is calibrated properly in an oversimplified world, this could be useful potentially. So yeah, I mean, for now, it just produces kind of a rainbow diagram. Oops. But it's a work in progress. So we'll see. And then in tandem to that self-organizing map component, I wanted to show proving grounds k-means clustering. They also have like a whole like range of components that you can start to use to cluster data and visualize it. And so in this case, you can use a k-means clustering to do something very similar, to basically group all the cells into clusters according to how similar their weights are, like the raw data, right? We keep talking about this raw data that represents each cell. So we can use that data, plug it in directly to proving grounds k-means clustering, and then we can get these various different clusters that start to tell you, okay, the red is program that is like similar to itself, and the same for every other color. So again, this is also, it can be useful. Right now it doesn't look like anything, but maybe it's the resolution of the thing. Let's bump it up a little bit. So again, yeah, in principle, what you do with the raw data is kind of, hasn't been figured out. But the idea is, let's start figuring that out, because I think there's a lot of data that's inherent in floor plans, even when you don't take into account many of the operational things. When you just take into account the configuration, there's a lot of raw data there that you can start to make use of. So, okay, so now it starts to look more like somehow the zones make more sense, right? You can start to see that these circulation areas are largely kind of in the same category. These east and west is kind of same in a similar category, and then this southern exposed part is kind of in the same category. So what is that doing for us? I'm not sure, but it certainly is starting to kind of cluster data that's like floor plan zones that are similar with one another. So yeah. And I think that's all I have for now, Carlos. Yeah, thank you.
Wow, thank you. Very, very cool. We have over 90 concurrent viewers and very nice feedback and comments like fantastic, mind-blowing, fascinating, interesting. Whoa, that's slick. So really, really cool.
Awesome.
Thanks for the presentation. And it's a free plugin, right? Right now?
Yes, absolutely. Yeah, you just have to go to food4Rhino and download it.
Perfect.
Yeah,
it's so great, our community and the ecosystem.
Yeah,
and well, greetings from all over the world, from Roberto, Aguito, Alessandro, Gautam, etc. So people from many different countries. Roberto Arguelles says it has a lot of potential, even more as a data generation for machine learning applications. Congratulations, Marco. It's a great work. Also, thank you from here, thank you from there. And some questions. Well, Brittany mentions, well, that I guess it's she, or she wants to try PlanBee. Carla, my colleague Carla, already placed there the link to download the application. And she says that I've used the ISOBeast plugin before to analyze viewing angles for a school project. That's another plugin, ISOBeast. I don't know.
Awesome. Yeah.
Mm-hmm. Yeah, Roberto asks if there is a way to change the color ranges in the analysis directly with the plugin tools.
Yeah, sorry, that's a no for now. We should look at maybe, not for now. I mean, you can do whatever you want with the raw values because they come out of the components normalized. So for example, you can take these guys and really quickly plug in a gradient component and create your own gradient. So that's the thought there with these normalized values. You can very quickly just, you don't have to kind of parameterize. You can just plug it straight in and it works. Yeah. Actually,
Mike Soderberg suggests to output the scores from 1 to 0 for each analysis. So you could use something like human to make a custom color scheme for a grid. That's
right. Okay. I'm not sure that I get that part. I mean, the values are between 1 and 0. It's just it is hard coded from black to white. So I guess you can add kind of a gradient input. I'll take a look at that. You would still have to kind of throw down a gradient, I guess, right? At some point. So that's an alternative would be to have it like built in, right? And you can just right click and select from a range of like 5 options, and that way it's just pre-built. So yeah, I think that's a good suggestion.
Perfect. Some more people are thanking you for the presentation. They say it was excellent. And another one says that the COVID idea is so practical. We'll try it later.
Awesome. Yeah, and there are probably better ways to measure these things. But yeah, if anyone has any ideas, what else can we be measuring with COVID? Obviously, a lot of it is maybe not in the domain of architects, but please send through some ideas.
Yeah, if you don't have Marco's contact email, go to the food4Rhino page, and then there is always a website and a support link where you can find his contact details. We should put it. We should put it also. Well, your contact details on the video description. Okay.
Okay. Yeah.
I think these webinars are great, not only for you, the audience, to learn about a new application, but also for Marco to get feedback from users.
Yeah, absolutely. I mean, this is honestly, for me, it's a very interesting topic, one that I don't get to do on my day-to-day because I'm building tools and stuff like this. But I think, maybe a lot of people are it's a very popular topic right now, kind of automated floor plans and these things. And this plugin doesn't do any of that, but it starts to put a number on the different parts of the plan, right? And so I think that's interesting.
And the example files or tutorial files are on your GitHub or on food4Rhino as well?
On food4Rhino. So let me just go.
So
let me go there.
So there is installer, and then there is a zip file or something like that with example files. Great.
Correct. And I've included the image because actually I didn't go over that. But anyways, you can there's an image there, and there's also a sample file that shows how you can upload a sketch. Here it is. So this is the component. So basically, you can feed it an image that you have on your C drive or anywhere. It takes a minute. Nice. And
nice, cool.
Yeah, and so anyways, you can get the polylines, and then you can literally like plug that into PlanBee for analysis, right? So, yeah.
Perfect. More comments. Angito Jatmiko says, I use ISOBIS, shortest path, and Sita before. This plugin is like compact version of them. Good work, Marco. Really appreciate it. We'll check your GitHub after this.
Yes, check it out. It's a public repository, and I think there's more to be gained from just leaving it public and hoping that people can contribute and benefit from it.
Mm-hmm. Do you plan to make it open source or?
It is. Well, it is open. Well, it is open source.
It is already.
And yes, so if you want to get involved in any way, let me know and contribute to it. So
feel free to contact Marco for any kind of support, but also if you are interested in being a contributor. More questions from this time from Mandar Campbell. Is there a way to connect the algorithm to a web page?
No, not right now. You can connect this to, you can open this in Rhino inside Revit and have it inside of Revit if you want to have it somewhere else.
So you have tried it already?
I haven't tried it, but all the Grasshopper plugins run inside of Revit, right?
Yeah,
so,
exactly.
I have yet to try it, but no, inside of the web, I guess I would have to kind of port it to be accessible on a website. For now, it's just
either using compute or maybe through Shapediver or something like that. But
yes, something to consider.
Yeah,
for sure.
Alfonso García from México. Saludos desde México. Muy interesante. Felicidades. Gracias.
Gracias, Alberto. Alfonso.
Alfonso García. Alfonso. Yeah. What else? Hi, Marco. Have you ever thought of implementing polygonal subdivision algorithms for the base structure rather than using a 2D grid voxels?
Polygonal, so like a Voronoi? Is that what the person?
Polygonal subdivision algorithms. I don't know if it's subd object or
I see. Or
mesh or a mesh.
Could it be like an octree type thing, or so something is different from a grid, basically? I guess.
Yes, something that is different from a 2D grid.
Yeah. I haven't thought about it. I think I use the grid as a starting point, just to kind of get the ball rolling. But if you have any specific suggestions of what you would like to see, I mean, I'd be interested in hearing that. And what would be the benefits? I guess you can describe a zone that doesn't have as much detail in more efficiently if you have less voxels, right? In that zone. So yeah, something to think about. If you have a specific suggestion, please leave it in the comments.
Yeah, my colleague Carla already posted your email address also on this chat.
Great.
Okay, thank you for this from Gautam Berebathula. It's difficult to pronounce for me. Then one question from Eleazar Coelho. Can be used with Rhino 5?
To be honest, I thought I would have to test it again. Let me get back to you.
I would recommend Eleazar to upgrade to Rhino 6 also because Grasshopper 1.0 is only available in Rhino 6. The version of Grasshopper you can use for Rhino 5 is old.
0. something.
Yeah, 0.976, something like that, right? But there is so much more on Rhino 6 that we really recommend all the people.
Yeah, honestly, I don't even have Rhino 5 anymore, so I haven't tested it in a while. Yeah. I believe it does run on Rhino 5, but don't test it.
Merci beaucoup pour cette représentation. That's in French, from BL Architecture. And second thing from a person that already asked something before, I understand why in the context of this plugin you are using path search based on the grid you generated. But do you have ever tried to implement vectorial shortest path search algorithm?
That's a good question. I recently was made aware of this stuff, of this kind of algorithm where you don't use a graph, but you just use kind of a heuristic algorithm where you what you described. You shoot rays. You shoot rays. If you have collisions, you kind of find a way around it, and so on and so forth. And it seems to be a very efficient one. I haven't tried to implement it, but maybe that would run quite fast. And I guess if you think about it, that's also kind of how people move, right? We don't move in a kind of predetermined. We don't understand the shortest path from the get-go. We have to kind of figure out the shortest path by walking. So yeah, I think that would be a good alternative to just having the current shortest path.
Okay. Maybe for next versions of PlanBee.
Yes.
One more comment and question by Mandar Campbell. Thank you, Marco. We are working to develop or collaborate on a workplace spatial planning tool to utilize in our business. Would you like to talk for collaboration on the same? Cheers. Well, as said, contact Marco, send him a private message and maybe explain your project, and maybe, I don't know, if Marco will tell you if he's open to collaborate, or if you can use same tools, or if he can develop some extra tools, right?
Yeah, sure. Send me an email, or again, feel free to just leave a comment in the chat, and I'll be in touch.
Okay. Now, Kate Reviakina, thanks a lot, Marco. Is there a detailed tutorial to distribute program based on weights you show in the last slides to understand better how to apply it? So a tutorial to distribute, detailed tutorial to distribute program based on weights.
Yeah, yes. I mean, the detailed tutorial, honestly, it's a bit of extrapolating you're going to have to do. So on the description here, when I first released plugin, I added a very detailed description. And so here there's a link to self-organizing, what a self-organizing map is. And so if you want to just understand that concept, actually that's just Wikipedia. There's another link right here that was shared with me when I was at the Bartlett. And it's a really good description of what a self-organizing map kind of does. And whether or not the self-organizing map is a good algorithm to apply to what we're doing here is a different question, because I think it needs more testing and stuff like this. But I would encourage you to go to the PlanBee description, click on this AI Junkie hyperlink, get familiar with what this is doing. And then once you've understood that, you can come back to these sample files, and it'll become a little bit more clear why the data is structured as it is. So, you're creating a kind of a vector, a multi-dimensional vector. So each cell contains 5 data points, right? Each cell is aggregating like these 5 different metrics. And by doing that, it's kind of it's a field of objects, similar to kind of the field that's described in this in the link that I just showed right here. So this is describing how these things are connected, and then how an initial starting point is determined, and how then the algorithm kind of refines its neighbors until it finds a feature map that is descriptive of that field. And so that's what this is doing. And so this file, again, you can find it on food4Rhino. And if you follow that tutorial and you come back and you look at this carefully, you can start to understand what's going on. And again, you can play with this kind of initial radius. And that's kind of the only thing you can do at the moment. It could well be that, I can expose more parameters. I just wanted to keep it simple. There's already a lot of inputs. And so yeah, hopefully that helps.
Yeah. Well, Kate adds that she's working on a big workplace project right now, and she would like to collaborate because until now she has been only using Galapagos. I hope Kate is a female name, because I'm saying he or she depending what I think, but if not, please don't take it wrong with me. Okay. So the person that made the previous version, because I don't know the name of the person because it's only strange symbols here, but he says triangulation plus quading the triangles. Usage case, visualization matches the geometry 1-to-1 plus having more resolution in areas that have more detail in them. This is related to the
grid.
Yeah, to the question before, with the vectorial shortest path algorithm.
Yeah.
To the previous question.
Right.
Well, I think it's better that he contacts you directly, right, with some more details.
Sure. So I think
you can have a private conversation about this.
Sounds good.
Different algorithms and ways
that sounds great.
to make the analysis. Well, Eleazar, she's from Venezuela. Gracias por tan interesante trabajo y presentación. Saludos desde Venezuela. Saludos a ti.
Saludos a ti. Yes.
And the last question from Xavier Tixon.
I recognize this name.
Okay, yeah. Okay.
Yeah, he's Xavier. I
It's
think
French?
Javier. He goes
Xavier,
by
Xavier could be. The name is different. Tixon.
Yes, he actually goes by Michael, but yeah. Anyways, you can call him Javier, it's fine.
Okay. We have Javier in Spanish, Xavier in Catalan, Xavier in French, right? And he says that AI Junkie is a great website. Amazes me how old and basic it is and how much information is available on it. I guess it's about artificial intelligence, right?
Yes, it's this website that I referred to that I haven't. Yeah, I've done a little bit of digging, but honestly, I'm not too familiar with it. I'm just familiar with this particular.
The design looks a bit old-fashioned, right?
Yes.
Really academic.
Yes. Yeah, I think so. And the last time it was updated,
we need to put attention on an interesting contents, not only on the design, right?
Yeah, in a way, the simple format makes it easier to focus on the content. So.
Fine. Yeah. And Kate, thanks you for the presentation and for answering the questions. Okay, Xavier says, hi Marco, haha, Xavier pronounced in a Portuguese way. Xavier, I guess.
Are you making that up?
A
little bit.
I don't know if it's Brazilian Portuguese or Portuguese from Portugal, because it's a bit different, right? It's like English,
sure,
like American English and British English.
Yeah, Javier, you're gonna have to teach me that offline, man. Yeah, I'm not sure how that's pronounced.
Okay. There are no more questions, and we are running out of time. But many thanks. We enjoyed the webinar a lot. It was very. I mean, we learned a lot, not only from your app, but also from the concepts you are trying to cover here. And yeah, maybe we can repeat the webinar in a few months when you have a newer version.
Yeah, I would love to.
Feel free to, contact us whenever you have a new version, and please update your food4Rhino app page. And to the audience, many thanks again for making this food4Rhino webinar series possible. And see you next week at 5 p.m. with a Panther webinar. This is a new plugin for jewelry based on Grasshopper.
Thanks again. Thanks, Carlos.
Have a nice evening or a nice day, depending on which part of the world you are, and stay safe.
Till next time. See ya. Bye.
Bye.